Yes, hello everyone and very good morning. Welcome to the live session where we are discussing reaction mechanism topic of organic, and it is very high scoring topic also. If you consider CSIR net exam, UPSC geoscientist gate exam, always some questions are asked from this topic, and in this topic the very important mechanism, which is the neighboring group participation, we have started little bit in the previous lecture. Now we are going to cover this mechanism into detail from this lecture. For you people, this lecture series will be complete in English medium only, so that the students who face Hindi language as a barrier should also able to get the concepts in their more understandable language, I can say that. So this will be our lecture number 2 for this week, and if I see overall, because we have started the reaction mechanism from the last week, so this should be lecture number, I think, 7 or lecture number 6 in continuation. If you are watching from the last week, then it will be lecture number 7, and for this week this will be lecture number 2. Today we are going to discuss about NGP mechanism. If you have watched the yesterday's lecture, you know what are the basics of an NGP, how a basic reaction of NGP takes place. We have classified this NGP into further subclasses also, so that it become easier for us to identify the question of neighboring group participation in the examination. So, I would like to first of all recap what we have studied in the previous lecture, then we will begin the today's lecture. Good morning Ankita, good morning Archana, good morning Mosmi, good morning Sunita, good morning The Moon, and good morning Priyanka. Welcome to the live session. I hope you enjoy watching the series and you learn in every lecture something new at least, and we will try that you are able to solve each and every question of your previous year exams. Okay. See, making notes and learning the concepts is a different thing, and applying the concepts in the question is a different thing. So, I am helping you out with the concepts, but you need to practice some questions. Then only you will be very fluent in organic chemistry. You will be able to solve some new questions. Your approach towards the new question will be better if you solve more and more questions in organic chemistry. You can solve some previous year questions also. You can go with reference book questions also. It depends upon you. Okay. सुप्रभात जी, सुप्रभात कैंप पैसिफिक, कैसे हैं आप? नहीं ज्यादा लेट तो नहीं हुए हैं. गुड मॉर्निंग विजय, गुड मॉर्निंग. So let's start the lecture. First of all, I will be doing the recap what we have studied in the yesterday's lecture. We have started with SNI mechanism, if you remember, and I stands for intramolecular. We see that there are three scenarios in which an SNI reaction can be asked to us, and the first one was when we will be having an SOCl2 with a 1,4-dioxane, that is ether, and of course the retention product is formed. In this type of mechanism, we saw that 2 times SN2 mechanism take place. That's why in the overall reaction, the retention is taking place. When we have a pyridine, only one time SN2 take place. That's why the product form is of inversion. And if examiner has mentioned only SOCl2 as a reagent, then also retention products are going to be formed. Moving ahead, we will look at the mechanism for each one of them. We have understood the mechanism. I think you have copied also. The important thing is when we use simply SOCl2, the Cl attacks from the same side as that of the living group. That's why a retention product is formed here also. In other two mechanisms, we have seen that I have explained you also. For example, in when we use ether as a solvent, 2 time SN2 reaction takes place. So overall retentions is observed, and we have done some questions also. This way, in Fisher projection also questions can be asked, where an examiner can set multiple options also by changing just the atom's position in order to confuse you. Then we have done question with pyridine case also. We have discussed now. Then we in the yesterday's lecture we have started with the neighboring group participation. We saw there are two necessary conditions. First, the neighboring group and the living group should be anti to each other. Then only neighboring group participation reaction will proceed. And second condition is that we have certain cases among which a question of neighboring group participation can be asked. For example, the case number 1 is of acetolysis, where a neighboring group is an OAC group and the living group is an OTS group. Similarly, we have a phenyl case, we have a bromine case. a non-boring case, and what is left is covered into miscellaneous part. This year also from miscellaneous we have one question. Every year NGP is asked in your exam because it's very important one. It's a very important mechanism to study. Okay, good morning Diksha, good morning to everyone who have joined. Amrapali, good morning. Sir, I missed the lecture by reason I covered all the previous lecture of the series. Okay, very good, Priyanka. Okay, so let's start. First of all, I want to give you a little look of a book, of a Claydon book. See what is happening here. Claydon says that if we have two types of group, we can understand these things very comfortably now. They are saying that let's suppose we have a living group Cl which is attached at the alpha position, and at the beta position let's suppose we have a group which has a lone pair, and they are comparing this rate with a simple group which has only a Cl group attached to an alkyl chain. Then they are saying that the first reactant reacts with water with a 600 times faster rate as compared to the second one. Now this we can understand very easily because in the first scenario there is a group which has a lone pair and it is eligible to behave as a neighboring group. That's why the rate of reaction is going to be very fast for the first case, because here the nucleophile is present intramolecularly, and first of all this is going to attack and the Cl is going to be removed. So whenever a neighboring group is participating in the reaction, the rate of the reaction is going to be very fast. This is what we are discussing in the lectures, in the basic portion of the NGP what we have started in the previous lecture. Similarly, they say that if we have an OTS group, let's suppose, attached to an alpha position, and the beta position has a phenyl group. Phenyl group of course has pi bonds. They are saying that this reacts with CF3COH, which is their nucleophile, 3000 times faster than this substrate which does not have any phenyl group. Again, this is happening because of this phenyl group which is eligible to behave as a neighboring group here. I hope you understand how fast a neighboring group reaction rate can be. And when we compare this, our case number third, if you remember of a non-boron situation, this double bond attacks into the OTS bond. Here this double bond is behaving as a neighboring group. We will see in detail how the products are formed, what are the intermediates, but for now just we are comparing the rate. Since this double bond is acting as a neighboring group, and in this situation we don't have any double bond, you can see the first reaction is going with a rate which is 10 raised to the power 11 times faster than the substrate which does not have any alkene. So these examples are very important which can be asked in your exam. This I have picked from Claydon book, and this is the scenario which we were discussing. Our case number 1 belongs to this acetolysis part only. When you see the first situation, what we have is an OTS group which is below the plane and OAC group which is above the plane. Correct? Now, since they both are anti to each other, yes, there is a possibility that neighboring group participation will take place. That's why if we compare the rate of the reaction, the first one reacts 670 times faster than the second scenario, because in the second one, there is no possibility of neighboring group to participate. It cannot attack into the sigma star orbital, no. It means here the mechanism will be a simple SN2 mechanism would be taking place, and the rate for this is going to be fast because of the neighboring group participation. Does it mean, sir, if any group present in the beta center has a lone pair, its rate of the reaction will be going to be high? No, this is not the case always. I repeat what I am saying. Do listen very carefully. What I am saying, at the beta center, if I place any group, any lone pair group, the rate of the reaction is going to be faster? No, this is not the scenario. There are few cases, or I can say there is one case is reported in the books also, which we will be covering in the miscellaneous part. What we have distributed here, if you remember this, yes. we will cover this parts into the miscellaneous, which show some exceptional behavior, you can say. We will be having a living group OTS only, and at the beta center we will place a lone pair group, but its rate of the reaction will not be high. It will be contradicting the NGP case. I will show you the example also. If you compare these two rates, they are saying we have a sulfur center at the beta. Let's suppose living group attached at the alpha center, and beta center we have a sulfur center. And let's suppose at the alpha center we have a OTS group. This is nothing but your OTS. It is similar to that OTS. And at the beta center you have a OME group. In the first scenario, it was expected that the rate of the reaction is going to be high, and it is happening also. The sulfur will attack and the Cl will remove. The Claydon is saying that it will react with water 600 times faster than the substrate which they are showing here. It is expected. Yes, sir, the lone pair is present here and it will attack. Neighboring group participation is taking place. But when we see the second scenario, what happens? The rate it reacts with ACOH 4 times slower. This is something which is not digestible. Can you see this? It is saying that it is going to react 4 times slower as compared to this. We have oxygen which has a lone pair. Then also in this scenario, when OMe is a neighboring group, rate of reaction is 4 times slower as compared to a substrate which does not have any lone pair group. So this particular scenario becomes very important. This year in December also, from this part only the question was asked. Though the question was little complicated, but it was a time taking question. It was not complicated. But once we place this OMe group a little further away, let's suppose this center was alpha, this will be beta, this will be gamma, and this we can call as delta. When this is a little further away, this OMe then behave as a neighboring group here, and this time the rate of reaction is going to be really fast. It is 4000 times faster than this group. It means when OMe placed at beta center, the rate of reaction is going to be very slow. It is not going to show NGP mechanism, but when we place it at the, let's suppose, delta center, or at the center which is eligible to form a 5-membered cyclic ring, the rate of the reaction is very fast, and this particular case is very important. So we will put some star over this. So when we revise our notes, we focus on this part. Did you get the contradiction? Why, how this OME case is different from other cases? We will be covering this part, but for now I have just given you a little bit introduction. We will go in sequence wise, otherwise if I straightforward start this OME case, there will be lots of confusion. First of all, what we are going to study is case number 1, case number 2, case number 3, case number 4. And then in the miscellaneous portion, there are further some bifurcations. For example, we need to study sigma bond NGP. We need to study that OME case, what we have just seen, that the rate of reaction at the beta center was very slow, but at the delta center it was very fast. That OME case need to be understood. Then a larger cyclic rings where NGP can take place, that we will study. So further this miscellaneous part will be bifurcated. So for now what we are going to do is we will start our case number 1. So let's start with case number 1. This was the question which I have given you as a homework also. I hope you must have formed the product. See, by looking the substrate, it is very clear that in the first scenario, the neighboring group and your living group are anti to each other. So here NGP mechanism is possible. Whereas in this case, since they both are not anti, here the NGP is not possible. So if any intramolecular reaction is taking place, of course, the rate of the reaction is going to be very fast as compared to the second one, and this we have just seen also. Now, what about the product, sir? How the product is going to be formed? See, we know that in the NGP mechanism, retention products are formed. So if we don't know the mechanism also, or if we do not want to do the mechanism also, we can draw the product directly. How we can draw them directly, sir? Let's suppose we have a 6-membered ring here. We know that OAC is a neighboring group. We will place this OAC as it is. OTS is the living group. Now, since we need to form the retention product, what I have done is retained the stereo of the living group, and in the place of living group, I have just placed my nucleophile and the product will be drawn. We got the product. This is how we can draw the product of NGP directly. Of course, I will be explaining you the mechanism also, but for now, we have drawn the product directly and it is a retention product. When I talk about the second scenario, what happens there? Since NGP is not taking place, in such a case, a SN2 reaction would be taking place. Now, if I draw the substrate once again at this center, what we have is OAC above the plane and OTS that is below the plane. Now, what happens? An ACOS, the nucleophile, will attack at the center and will remove the OTS group. So, the product is going to be of inversion because in SN2 reaction, always inversion takes place. So, what we observe is a 6-membered ring, OAC that is above the plane and OAC that is below the plane. And of course, this product is of inversion. If you compare both of the products, if you compare P and Q, what you find is the P product is same as that of Q product, but the P has been formed by a different mechanism, that is NGP, and the Q has been formed by a different mechanism, that is SN2. So without drawing in the chair form also, or without doing the mechanism, we can solve the question. We can draw the product. But if examiner will go in detail, he will go into the chair form, or he wants to know about the chirality, he wants to know about the racemic mixture is forming or not, then we need to understand this question in little bit depth. So if you have understood this, then we will move ahead and we will draw these substrates into chair form and we will try to solve this their mechanism also. See, we have two substrates here, a 6-membered, so I will be moving on a blank slide. So let's suppose I have a chair form. Now at this center I have placed an OAC group at an equatorial center, and at this center I have placed my OTS group at an equatorial center. If you look properly, this is above the plane and this is below the plane. U stands for above and B stands for below. My first choice was to keep both of them at the equatorial center. So I have kept them at the equatorial center. This was the scenario. If I look at the substrate, the OAC was above the plane and the OTS was below the plane, and I have kept both of them at the equatorial center because this would be our first choice looking at the stability. But in such a scenario, they both are not anti to each other. What I am trying to say is its sigma star orbital is present somewhere here and its oxygen lone pair of the OAC group. If I expand this AC group, what we find is it looks like this. Now this lone pair is not able to approach into the sigma star orbital, means this form is inactive towards the NGP mechanism. But we all know that every chair form do undergo flipping. It means this particular ring can flip. So it's our responsibility to flip this chair form. What we do in flipping, sir? Simple. Every axial substituents become equatorial and every equatorial substituents become axial. And we move one carbon center ahead. So this carbon center will be moving at a one center ahead, that is at this center. Since OTS was their equatorial, now it is going to be an axial center. Now in the second scenario, OAC group was at equatorial, it is going to be placed at an axial center. This is how they are going to look. Now they are in a perfect scenario that the OAC oxygen would attack into the sigma star orbital and the lone pair present here will attack into the sigma star and the OTS will be removed. Yes, this form will be active towards the NGP reaction, though it will be present in little lesser percentage, but this form will be active towards the neighboring group participation because the sigma star orbital and the OAC lone pair is very much approachable. Did you understand? Now, once the group has attacked, the OTS is going to be removed and we are going to generate a cyclic intermediate. So, how the cyclic intermediate is going to look, sir? Let's see. We have a chair form. From this center, we have above the plane, we can say oxygen, a group. A bond has been formed at this center. This forms three bonds, so it will be having a positive charge and a CS3 group will be present here. I can convert this into a normal chair form also or a normal cyclohexane form. Now this cyclic ring is formed from above the plane, no? So I will be drawing an above the plane oxygen here, above the plane oxygen here. What I am having is I will close this ring, a CS3 group present here and a positive charge here. This is what it is going to look in a cyclohexane form. I can also draw resonating structures for this. This lone pair can move here and this will shift at the center. So a six-membered ring, an oxygen, six-membered. Of course, I am going to close this ring and the positive can move at this center. So this will be our first resonating form and this will be our second resonating form. I can draw for both the structures and resonance a hybrid form also. I will go into the depth of the mechanism so that nothing is left. Examiner, if asked some question from this part, it will be in your notes only. Okay. So I can draw the resonance a hybrid structure also. What is a hybrid structure, sir? Means we are going to represent both of these structures into a single form or a single structure. So I will be showing a dash bond here, a dash bond here, and a positive is delocalized. It is on the top oxygen or it is on the bottommost oxygen. This is how it is going to look, sir. Now, from here, we can draw two products. One, when we attack at this center, let's suppose our ACOH is attacking at this center, this ring will be open. Or I can explain you from the resonating form also. Let's suppose my nucleophile attacks here and the rings open. So the product from the second resonating form would look like we will be having a below the plane OAC group and an above the plane and OAC group. Okay, and if I draw the product from the first form, the attack will take place from the bottom structure or I can say from the bottom center. So below the plane OAC will be at this center and above the plane OAC will be at this center. So there are two products which we are observing. First is our P and second is our Q. Are you able to digest that yes, the product's photograph is going to look like this? The products are going to look like this. Are you able to digest this concept? And can you tell me what is the relationship between the two products which we have drawn, the P and the Q? Tell me fast. The intermediate has plane of symmetry, pair of uniform. Very good. Excellent, Camp Pacific. In the further cases, I will be drawing an conclusion also and I will be coming back to this example and I will show you that you need not to form the products and you need not to compare the relationship. By just looking at the intermediate, you can tell whether the products are going to be pair of enantiomers or whether the products are going to be identical. But once we finished with the case number 2, then only we will be able to do that. But for now, we have gone into a detailed version of this question. Yes. So what's the relationship between P and Q? This question becomes a question of, I can say, a stereochemistry where you need to form the relationship between the products. Sometimes people say that they are identical in nature because they think if I flip the first molecule, if I flip the P molecule, it is going to become a Q molecule. But have a look carefully. If I flip this molecule, this center will be moving at this place. Since the OAC is present above the plane, after flipping at this center, we will be generating an OAC that is below the plane, but you have a OAC present here that is above the plane. So how they can become identical? Are you getting my point? Spread piece. If you flip the first molecule, what is going to happen is you will be having a six-membered ring, and at this center, the below the plane substituent will be present, but you have an OAC that is above the plane. So you cannot say that they are identical. They look like identical, but they are not identical. So when you find the relationship between the two, they are going to be pair of enantiomers. Once I have drawn a conclusion in the case number 2, then you need not to find such relationship. Also, by just looking at the intermediate, you will be telling that yes sir, the product is going to be identical or the products are going to be enantiomer. Okay, this will be very easy. For now you need to do some stereochemistry part. The products are going to be pair of enantiomers. And if you form a pair of enantiomers, let's suppose in uh, equal percentage, because 50% chance is to form this product and 50% chance is to form this product. If two pair of enantiomers are present in equal amount, then can you tell me the final solution is going to be what? This very famous term used for this. In previous year questions also examiner give this terms. Very good shopping era. Sir, in such a situation, the products are going to be a racemic mixture. Now tell me whether the racemic mixtures are optically active or the racemic mixtures are optically inactive. What's the scenario? Very good. Always the racemic mixture forms are optically inactive. So in this scenario, once you form the final product, this is going to be optically inactive. See, if this question comes into part B of CSIR net, you can say of in 2 marks, then they are going to just ask you about the rate or they will just ask you about the product. If they go into depth of the topic, then they will ask you about the intermediate, they will ask you about the relationship between the product, they will ask you whether the final solution is optically active or inactive, they will ask you how the chair intermediate is going to look. So we need to understand this concept or this question into a really depth version of this question. We should get that points. So this was the first scenario where we have an OTS and an OAC group anti to each other. Now what happens if we have both syn to each other? So again we will be drawing a chair form in order to get the concept. Let's suppose we have a chair form present here. Okay. So now for this scenario what we have is where the question is OAC is placed above the plane and the OTS is placed above the plane. Okay. So what I have done is I have placed at this center OAC above the plane. I have kept this at the equatorial center and the OTS is also above the plane. So this will automatically go at the axial center. Now, when I check the sigma star of the OTS, it is present somewhere here and it is not possible for the OAC group to attack into the sigma star orbital since they are not anti to each other. The sigma star orbital will not be approachable by the oxygen lone pair. Such type of attack cannot take place. Then a point comes in our mind, sir, of course this ring might flip. Okay, then we will flip also. Let's suppose I have done the flipping. What happens in the flipping? Sir, axial centers get converted to equatorial center. So I will be having a OTS at this center which is equatorial. Moving one center ahead, I will be having a OAC at this center, which will be again axial. If we look at the sigma star orbital, it is present somewhere here, and this type of approach again is not possible because this is below the plane, that is above the plane. So since they are not anti to each other, no NGP or neighboring group participation can take place in both of the forms of the chair. So in such a scenario, what happens is our six-membered ring, I will be drawing the substrate once again. Let's suppose I have drawn the second one with the OTS above the plane and the OAC group present here above the plane. Now the nucleophile will come and it will simply attack into the sigma star orbital and OTS will be removed. And now the mechanism followed is going to be simple SN2 and the product is going to look like, so we are having a center here which will be our OAC group, and of course since attack has taken place from the below the plane, so at this center we will be having a below the plane OAC group. If I convert this product into cyclohexane form, what I have is a OAC above the plane and a OAC group that is placed below the plane, and this is our product, and of course this is a single product which is of inversion. Did you get the complete concept of this question? Rate we have compared. Yes, the rate of the substrate which is undergoing an NGP mechanism will be faster as compared to that of SN2 mechanism. So this was the complete picture of an acetolysis reaction for case number 1. The case number 1 is finished. We will be coming back again by when we have understood the conclusion portion, so that we can form the products in a short way also. But for that we need to cover case number 2 where we have phenyl rings as a neighboring group. Okay. So whenever question is asked, they will try to ask you about whether the product is of inversion or retention. They will ask you whether the products are pair of enantiomers or you have formed an identical product. This type of questions are asked in your exam. Moving ahead, we will be starting with case number 2 now. If you remember the chart in case number 2, what we are going to get is a OTS group as a living group which is present at the alpha position, and this time a phenyl ring will be present which will be behaving as a neighboring group. This same concept is mentioned in the Clayton book also, but they have complicated it a little bit. We will understand this in the most easiest way. See, let's take a very simple example without any stereochemistry, so that first of all we understand what happens when a phenyl ring behave as a neighboring group. Let's suppose we have the same question. I'm writing here also. We have a OTS group and a phenyl ring is present as a neighboring center. They both are anti to each other and we have a nucleophile ACOH. Since the sigma star orbital will be present here, it will be very easier for the benzene ring to attack into the sigma star and remove the OTS group. Yes, the double bond of a phenyl ring is going to behave as a neighboring group. Once this happens, we will be forming a 3-membered ring, sir, and a 6-membered ring will be attached from this center. Since the double bond has attacked, so positive charge will be present here and a double bond will be here. If I draw the resonating structure, this double bond shifts here, so the positive will be formed here. If this double bond shifts here, the positive will be formed here. I can also draw a resonance, a hybrid structure for the same, a 3-membered ring, a 6-membered ring. I can say a dash line is present here where a positive charge is delocalized. This type of intermediate where a phenyl rings participate has a name also, and it is called as phenonium ion. This type of intermediate is called as a phenonium ion. Very good. Now, when we have a nucleophile, let's suppose an ACOH nucleophile is present, it can attack at two centers. I'm explaining you via this. Let's suppose this is A and this is B. Attack can take place at the B center and the attack can take place at the A center. Let's suppose if we attack at the B center, the aromaticity of the phenyl ring will be regained and we will get our product. Let's draw both the products which which we will be getting. Let's suppose when we attack at the B center, the product will be an OAC group present here and a phenyl ring present at this center. And in the second scenario, when I attack on the A center, our OAC group will be present here and the phenyl ring will be present here. Since we have formed both the products, and if I ask you what will be the relationship between the two, you will be saying, sir, they both are same, identical, because once I rotate the first molecule, it becomes the second one. So without any stereochemistry, it's very easy to tell they are same molecules, they are identical, or I can say they are homomers. This is the simplest case of a phenyl ring behaving as a neighboring group. And this is not going to be asked in your exam. This is simply to understand the concept. Moving ahead, when I will be placing some stereochemistry part in this, the question becomes really very interesting. Should I move ahead? Let's discuss a case with stereo also. Let's suppose we have a same question where we are having a OTS group as a living group and a phenyl group is present as a neighboring group. Someone has placed two substituents. Let's suppose a methyl which is above the plane here and a hydrogen which is below the plane here. And again at this center we have a methyl that is above the plane here and a hydrogen that is below the plane here. And we have a ACOH. Now what happens if we draw the product? Let's see. Again, the same phenyl ring is going to attack at the OTS center and it will be removed, and we will be drawing the phenonium ion, which will be similar to the case we have drawn just now. Again, the positive charge will be delocalized at the three centers. Now, what we have to do with the stereochemistry, sir, how the substituents are going to be placed. If the methyl was present in the question as above the plane, we will be keeping this methyl above the plane and the hydrogen as below the plane. Similarly, here also, the methyl was above the plane and the hydrogen was below the plane. So, we will be keeping this in the similar way. Of course, this type of ions are called as phenonium ions. Phenonium ions. Now, when my nucleophile comes, it can attack at two centers. At B center, aromaticity will be regained from this side. A center, it will be regained from this side. What I am going to do, I will be drawing both the products, and now it's our responsibility to compare the products relationship, or the what will be the relationship between the products. Let's suppose if I attack from A center, my OAC will be present here and my phenyl ring will be present at this center. Now what I am trying to do is, with the stereochemistry remaining the same, try to look a Y at this center. So my methyl will be above the plane and my hydrogen will be below the plane. Again at this center, my methyl will be above the plane and hydrogen will be below the plane. I hope you are able to you are able to see a Y in the stereo part. Similarly, I will be drawing the product at this center also. My OAC group will be present here and my phenyl ring will be present at this center. The stereo says that we have a methyl above the plane and we have a hydrogen that is below the plane. Similarly, here also we are having a methyl that is above the plane and a hydrogen that is below the plane. Now this question has become of stereochemistry. You need to tell me what is the relationship between the products P and Q. Are they similar? Are they enantiomers or are they diastereomers? What do you think? What will be the relationship between the two products? According to Mosumi, it is identical. Okay, Diksha is saying, sir, enantiomer, racemic mixture, or chiral enantiomer. Very good, Diksha. Enantiomers. Okay, do give your answers. Priyanka is saying enantiomer. Akansha is saying identical. Enantiomer. Enantiomer. See, in stereochemistry, when we study about a topic that is relationship between the molecules, how we can find that is, if we find that whether these two molecules are mirror image of each other or not, I have placed a mirror between the two molecules. What I find is this phenyl is looking at the phenyl, this hydrogen is looking at the hydrogen, this methyl is looking at the methyl, and at the centers which are behind hydrogen below the plane, they're also below the plane. It means yes, these two molecules are of course mirror image to each other. If two molecules are mirror image of each other and in any one of the molecule plane of symmetry is absent, then the relationship between the molecules is going to be enantiomer. Since in this molecule plane of symmetry will not be present, so the relationship between the molecules will be pair of enantiomer. If you are not familiar with this technique, I can use the traditional one also. What we do is mirror image non-superimposable. That this is what the definition of enantiomer says. Yes, they do both the molecules are enantiomer of each other. Sorry, mirror image of each other. And if we pick the first molecule, place it on the second molecule, they are going to be non-superimposable. So yes, the definition also satisfies, and we can say that these two molecules are actually pair of enantiomers. Finding RS configuration will be a very lengthier method. That will be our last option to do so. But there are other shortcut methods also which we must know in order to find the relationship in a very quick time. Yes, but keep that option, the very last option, shopping era, to find the RS configuration. Try to solve the question without RS because it will save your lot of time. So the relationship between these two products are going to be pair of enantiomer. Now what if I ask you what will be the final solution, whether it is going to be optically active or inactive? What will be your answer? If I ask you about the final solution being optically active or inactive, if it is pair of enantiomer, then there is 50% chance to attack at the A center and 50% chance to attack at the B center. So if two pair of enantiomers are present in equal amount, then of course they are going to form racemic mixture. And of course racemic mixtures are always optically inactive because they do not rotate the plane polarized light. So this are the further conclusions which we can draw. Pair of enantiomers, racemic mixture, optically inactive. This A and B centers looks like to be a similar one, but actually when we form the product, they are different. Okay. So this is how our product is going to look. Now let's take another scenario. I will be giving you 2 minutes time to solve this question, and you need to tell me what is the relationship between the two products if I just change the stereochemistry in the starting material. Let's suppose I have a OTS center. In this scenario, I have a below the plane methyl here and above the plane hydrogen here. Now tell me what is the relationship between the two products you are drawing in this case, and also tell me when I see the final solution, it is actually optically active or it is optically inactive. Yes, take 2 minutes to solve this question, or you can take 3 minutes also. Tell me fast what will be the relationship between the molecules or either products. Very good. No POS intermediate identical optically active. Chiral intermediate identical product optically active. Excellent. You people know the shortcut way also. Hmm. Inversion, optically active. What does inversion means here, Priyanka? Means the product formed here are of inversion. Chiral, identical, optically active. Very good. See, again, the phenyl ring is going to participate. It will attack at the center and the OTS group will be removed. We are going to generate a six-membered ring, a phenonium ion, where the positive charge will be delocalized. So I have drawn the resonating form only. And at this center, we have a methyl that is above the plane and a hydrogen that is below the plane. Here the scenario is little bit different. We have a methyl placed at the center that is below the plane. Now once the nucleophile comes, it has two options to attack at the A center or either at the B center. The ring aromaticity is regained from both the centers. Let's draw the two product P and Q. For the P, let's suppose attack has taken place at the A center. My OAC group will be placed here and the phenyl ring will be placed here. Try to look and find a Y at the centers which I am drawing. I have a methyl that is above the plane and I have a hydrogen that is below the plane. At this center, I will be having a hydrogen that is below above the plane and a methyl that is below the plane. In the second scenario, my OAC will be placed at this center and my phenyl ring will be placed at this center. Again, the stereo remains as it was. Here we have a methyl that is above the plane and a hydrogen that is below the plane. Placing hydrogen here above and a methyl at below the plane. Now you need to compare the relationship between the two molecules. If I hold the first molecule from these two centers and I give a rotation of 180 degree to the molecule, what is going to happen is this carbon will be coming at this place. It means this is 1, the 1 will be placed at this center and this carbon will be coming at this place. If this is 2, the 2 is going to come here. The backbone, which is of black in color, is going to be completely similar to that the case of second one. What about the substituent, sir? If I rotate this methyl 180 degree is complete molecule, the methyl which is placed above the plane, after a 180 degree rotation, this is going to be placed below the plane. And this is what we find here. Similarly, this methyl which was below the plane, after 180 degree rotation, it is going to be placed above the plane. What we find is if we rotate the first molecule, it looks exactly similar to the second case. It means the relationship between the molecule is identical. If I change the stereochemistry in the starting material very slightly, just changing the methyl stereo, the product's relationship has also been changed. So these are going to be identical in nature. So now if I ask you whether the final solution is going to be optically active or inactive, then what you are going to say? See, both are similar products, so I can find whether this product is optically active or not. What we find is this does not have any plane of symmetry, this does not contain any center of symmetry. It means it is optically active. So the final solution is also going to be optically active one. Did you get this concept or not? Very good. So of course, the final solution is active. Now, we are going to draw a very important conclusion which will save our time in telling whether the final solution is active or inactive. We need not to draw the product. We can directly tell whether it will be active or inactive. This conclusion we will use in addition reaction also. This we will use in sigma bond NGP also. And the case which we have just discussed, the acetolysis, there also we can use the similar conclusion. They got the concept, but hmm, What you have written, your comment is not visible to me. But got the wrong, okay. You didn't get the identical, but you got the similar product. Okay. See, let's come to the final conclusion part. We have drawn two phenolium ions, right? The first one was like this, where both the methyls were placed above the plane and above the plane. And the second scenario was like this, where at one center we have a methyl above the plane and at the second center we have a methyl below the plane. This was the in the first question and this was in the second question. Now, I am trying to ask you, tell me whether this is optically active or inactive, whether these intermediates are active or inactive. How you are going to check? Again, use symmetry elements, what we study in stereochemistry. Tell me fast whether the first one is going to be active or inactive. Yes, the first one is going to be inactive because if we place a plane here, of course a plane of symmetry is present. So the first one is going to be optically inactive. What about the second one? We have four symmetry elements: plane of symmetry, center of symmetry, axis of symmetry, and alternate axis of symmetry, which we study in stereochemistry, which we use to tell whether the following molecule will be active or inactive. For the second scenario, if we look, we don't have any plane of symmetry because once we draw the plane, this methyl is above and this is below. They are not going to reflect to each other. So plane is absent. And if we talk about center of symmetry, this is definitely absent. The molecule is going to be optically active. Now, sometimes students get confused. Tell me whether this molecule will have a C2 axis of symmetry or not. Tell me whether this molecule has C2 axis of symmetry or not. Does this have C2 axis of symmetry or not? What does C2 axis symmetry mean? If I place a axis and I give a 180-degree rotation, then can I get the similar product or not? Let the axis would pass from here only. This is how our axis is passing and I am giving a 180-degree rotation at from this center. Yes, of course, in such a scenario, sir, your methyl which is placed above the plane here will be rotating 180 degree and will go below the plane there. I can give you a simple example also. Let's suppose I was having a methyl here and a methyl here. In this version of the reactant, you can very easily understand this. What I have done is placed a axis here. I have given a 180-degree rotation. Now this methyl which is above the plane, of course this is going to go below the plane and this one is going to come above the plane. They both are similar molecules. Then yes, the axis of symmetry is present. If a symmetry element, that is axis of symmetry, is present, then why I am calling this molecule as optically active? This is also a confusion which students face. Can you tell me, yes, axis of symmetry is present, then why I am calling this as optically active? What's the hidden concept here? Do you know that point or not? Because it rotates plane polarized light. Yes, we can say that, but this is not the correct explanation. Relate with the axis of symmetry. Why axis of symmetry is present, but we are calling this as an optically active. In this, not in this scenario, in each and every scenario, let us take any molecule. If axis of symmetry will be present and it does not have a plane or center, we are going to call that molecule as an optically active. Why? Axis of symmetry is not taken into consideration. Always remember, not only just C2 axis of symmetry, Diksha, axis of symmetry never decides the chirality of the molecule. Please note it down here. Axis of symmetry never decides the chirality of molecule. You cannot decide on the basis of axis of symmetry whether the molecule is going to be chiral or it is going to be achiral. Okay, this axis of symmetry does not play any role in deciding the chirality. This point is also important. Sometimes students get confused. They come to me and say, sir, the axis of symmetry is present, then why we are calling this as chiral? Because it doesn't play a role in deciding the chirality. A molecule can be chiral and it may have axis of symmetry and it may not have axis of symmetry also. Okay. Such type of molecules which do have axis of symmetry and are optically active are called as disymmetric molecules. Okay, this is a portion which we usually cover in stereochemistry, so I am not going into the depth of that topic. Okay. So now coming back to our part, that is, yes, we have find that since this is optically inactive, plane of symmetry is present and this is optically active. So what a conclusion I am drawing here is, let's suppose if you are solving a question and you get an intermediate, and if your intermediate is optically inactive, your cyclic intermediate is optically inactive, then in such a scenario, the products which you are going to form from here are going to have a relationship, that is pair of enantiomers. Is this will follow, sir, in each and every case? Yes, in every case. If the intermediate is optically inactive, the product will be formed and they will be have a relationship of enantiomers. And enantiomers always form racemic mixture and the final solution is going to be optically inactive, all in one go. And if, let's suppose, your intermediate is optically active, then in such a scenario, the relationship between the products is going to be identical. You can cross check your answer from this or you can directly take your option from this. And if the product has been formed identical, then please check whether the products which you have formed is a meso compound or not. If the products are not a meso compound, then of course your relationship between or your final solution is going to be go optically active. And if the product you have formed is a meso compound, then they are going to be optically inactive. This is a new version which I have added here. You need to also check whether the compounds or the products which you have formed does fall in the category of meso or not. If it does not falls in the category of meso, your final solution is going to be optically active, and if it falls, then it will be optically inactive. But the relationship is going to be identical, no doubt in this. So these are the two conclusions which I will be using again in the addition reaction part. Sigma bond NGP and the case which we have just discussed now can be also explained on the basis of this. Did you get this concept? Did you get this conclusion portion or not? Do tell me in the comments. Did you get this axis of symmetry part? Each and everything, small points should also be clear in this slide. Got this? See what happens now when you study a book. Let's suppose if you study the Claydon for the same example, they will explain you the concept, but they will not go into the depth of the concept so that you are able to dig each and every point out of the question. That's there a teacher helps you because um, we have linked the concept of stereo also, we have linked the concept of other topics also, so that you can understand the topic in a very holistic way. Okay, sir, एकदम चमक चमाचम चमक गया गुरुजी. चमाचम चमकाएंगे कैंपस पे, लेकिन जब हम हिंदी में लेक्चर लेंगे तब चमकाएंगे। अभी फिलहाल थोड़ी मजबूरी है, तो अभी तो इंग्लिश में ही लेक्चर है, तो चमाचम चमक गया। चलो बहुत बढ़िया। अब इसके बाद हम कुछ क्वेश्चंस भी करेंगे, वी विल डील विद सम क्वेश्चंस आल्सो। पर अगर हम प्रीवियस वाली सिचुएशन को देखें, इफ वी लुक एट द केस व्हिच वी हैव डिस्कस्ड just now, this was the cyclic intermediate which we have formed. If I draw a line, a plane like this, then of course this intermediate do have plane of symmetry, and if it is optically inactive, we can straightforward tell that the products are going to be pair of enantiomers. No need to draw the product, no need to tell anything, check the relationship. We can straightforward, just looking at the cyclic intermediate, we can say yes, the products are going to be pair of enantiomers and they are going to form a racemic mixture. Final solution will be also optically inactive. Do you understand how I use that conclusion in this question? Now it becomes very easy to just, we have to check the plane of symmetry or the chirality in the cyclic intermediate. Okay. Sir, please tell me the chapter number in the Claydon. I think the chapter name is rearrangement. I am going with the old version of the Claydon. I have studied in my time the old version only, so I till date I prefer the old version. There is some extra content in the old version and some contents have been eliminated in the new version. That's why I recommend and I prefer also the old version of the Claydon. Chapter number I think 36 and the chapter name will be rearrangement. Okay. सर इंटरव्यू में कैसे क्वेश्चंस पूछे जाते हैं? लॉजिकल क्वेश्चंस पूछे जाते हैं, जैसे आई कैन शेयर यू एक्सपीरियंस ऑल्सो। वन ऑफ माई स्टूडेंट व्हेन वाज गिविंग अ टिफर इंटरव्यू, उनसे पूछा गया कि डू यू नो अबाउट, देखो डिपेंड करता है आप किसका इंटरव्यू दे रहे हो, पीएचडी का इंटरव्यू दे रहे हो, बार्क का इंटरव्यू दे रहे हो या कोई और इंटरव्यू दे रहे हो, तो इट डिपेंड्स अपॉन द इंटरव्यू ऑल्सो। I am telling you experience of PhD. One of my student when was giving an interview of for TIFR, there she was asked, you have studied Robinson annulation, remember? She was asked what's the reagent involved in the Robinson annulation, how, what are the reactions involved there. So this type of questions they ask. Once you explain this, then they will go further deeper with your answer only. They will ask you further questions what you have explained. So do speak that thing into anything in the interview if you are very much clear and your concept is completely clear about that topic, then only use that concept into your answer, because a question will come again what you have just answered. From that portion only they again ask question again. Okay. Okay, so let's wind up for today. This is what we have kept for today. In the further lectures, I will be moving ahead from this. And in the next lecture, we will be covering our case number 3, 4 and the miscellaneous part. Thank you so much for today. Let us wind up, and I hope you enjoyed today's lecture. You got to know, you got to learn something new things. Thank you so much. Take care. Bye bye and happy learning.